Hello, today we will cover section 12.5, related rates. Just like the section on optimization, we have a strategy for solving related rates problems. In your book and in real life, most of the problems will be presented to you in words, and you will have to figure out how to formulate the mathematics and then analyze the mathematics in order to come up with an answer to the problem. So, just like with the optimization problems that we've already considered, here's a strategy that you might follow when attempting related rates problems. Obviously, you read the problem. In a lot of situations, a diagram might be helpful. Next, I would suggest introducing suggestive notation. For example, if one of the quantities of interest is profit, call that P. If one of the quantities of interest is area or volume, you might label those as A or V. Next, figure out what you are given in the problem and also what the unknown is, and then write those quantities in terms of your notation. We will want to relate the quantities that we've introduced, and then really what we're after in this section is relating the rates. And so keep in mind that for us, a rate is a derivative. In particular, in this section, all of our quantities will be functions of time. And so the rates that we will be concerned with are derivatives with respect to time. As such, once we have our equation relating the quantities in part 5, we will use implicit differentiation that we just discussed in order to get the derivatives with respect to time into the problem. Don't forget to use the chain rule when differentiating. At the very end of the problem is when we enter what we're given and solve for the unknown. Today we will work through 2 examples to show you how this strategy plays out. The first example is a review problem from chapter 12, in particular number 71. Here we're given a profit, P, in units of dollars that we obtain from selling X cups of latte at a particular company. As you can see, the profit is a quadratic function of X. And then we're told that when final exams start, the demand, in other words, X, is exactly 450 cups of coffee, and it's increasing at a certain rate. In other words, the derivative of X with respect to time is 90 cups per day. What we're going to do in a second is figure out what dP/dt is at the start of final exams. To emphasize, dP/dt is the rate at which the profit is changing with respect to time at the particular instant. In other words, at the start of final exams. In this problem, a diagram isn't really necessary. And in particular, we are already given an expression relating our quantities of interest. Even more, those quantities have already been defined for us. Our relationship of the quantities here is P equals minus x squared divided by 360 plus 6x minus 300. And what I'd like you to do is keep in mind that P is really a function of time, and so is X. Right? The number of cups that we're selling might change depending on what day it is. The profit will change depending on how many cups we sell, which depends on the number of days, and so we can think about the profit also as a function of time. In order to get the rates into the problem in a moment, we will differentiate this equation with respect to t. But maybe first, we will write down what we're given. In the problem, they tell us that dx dt is equal to 90 cups per day at the moment when x is 450. And the unknown, what we will eventually solve for in this problem, is dP dt, the rate at which the profit is changing. And I want to know that at the moment when x is 450. In other words, when final exams begin. As you can see in the equation, we don't have any derivatives at the moment. We just have p and x. But of course, we're given information about the derivative of x, and also we want to find the derivative of p. In order to get the derivatives into the problem, we have to differentiate the given equation with respect to time, with respect to t. We do this with implicit differentiation. I'm going to differentiate the left-hand side with respect to t, and I'm also going to differentiate the right-hand side with respect to t. On the left-hand side, the derivative of p with respect to t is just the quantity that we're looking for, dp dt. On the right-hand side, whenever I differentiate one of these x terms, because we're differentiating with respect to t, I'm going to have to use the chain rule, because we are doing implicit differentiation. In other words, the derivative of minus x squared over 360 is minus 2 over 360 x, and then times dx dt by the chain rule. Since we're adding, we can add the derivatives. The derivative of 6x is 6 dx dt. The derivative of minus 300 is 0, because 300 is a constant. At this point, after differentiating, we now have the rates in the problem, dp dt, which is unknown, and then dx dt. Our very last point of the strategy is to plug in what we're given, and then solve for the unknown. So in particular, dx dt here and here equals 90, and then x is equal to 450. So if I substitute those quantities in, I get dp dt is equal to minus 2 over 360 times 450 times 90 plus 6 times 90. And if we evaluate this, we can figure out the value of dp dt. So with a little bit of cancellation here, 2 times 90 is 180 over 360. So that will simplify to minus 450 over 2. 6 times 90 is 540. Negative 450 over 2 is negative 225 plus 540. And so the value that we're getting here is 315. And the units of this are the units of dp dt. In other words, dollars per day. The next problem is a problem that maybe oil production companies might have to consider. In this particular problem, we have an oil spill, or an oil slick apparently, in the Gulf of Mexico. We're going to assume that this slick is a disk, so it's in the shape of a circle, and you might remember that the area of a circle is pi times the radius squared. The units of our area in this case are square kilometers. The radius is given to us in kilometers. And what we're looking for is the rate at which the area of the oil slick is changing at the moment when the radius is 2 kilometers. And not only do we want to know at the moment when the radius is 2 kilometers, but we want to assume here that the radius is increasing at 0.3 kilometers per day. Like with our previous problem, a diagram is probably not necessary for this question, but I'll go ahead and sketch one anyway. So here's our oil slick in the shape of a circle. The radius we're given in the problem is lowercase r. And we're also told the relationship between the quantities of interest is the formula for the area of a circle. A equals pi r squared. Like in the previous problem, the quantities A and R are both functions of time. The oil slick is expanding, so the area is getting larger, as is the radius. In this question, the information that we're given is the rate at which the radius is changing. In particular, the problem tells us that dr dt is equal to 0.3 kilometers per day. We're told that the rate is changing, the radius is changing at this rate at the moment when r itself is 2 kilometers. The unknown, what the company cares about in this problem, is how quickly the area of the spill is changing. Like how quickly is this oil slick growing in area? And so in particular, since it's a rate that we're looking for, we want to know a derivative, dA dt, at the moment when r is 2. The relationship A equals pi r squared relates to quantities that depend on time. We want a relationship between the derivatives. To get that, we differentiate implicitly with respect to time. Just like in the previous problem. Differentiating on the left, we have ddt of A, and on the right-hand side, we have ddt of pi r squared. The derivative of A with respect to t is just dA dt, the unknown quantity. On the right-hand side, this r depends on t, depends on time. So when we do the derivative on the right-hand side, we need to use the chain rule. We will end up multiplying by dr dt. Pi is a constant multiple, and so that can be factored out of the derivative. What we have on the right-hand side then is pi times the derivative of r squared with respect to t. The derivative of r squared is 2r, but then by the chain rule, we have to multiply by the derivative of r with respect to t. The last step in the strategy is to plug in what we're given. We are given dr dt is 0.3 and r is 2. And so we get dA dt is equal to pi times 2 times 2 times 0.3. 4 times 0.3 is 1.2. And so we're getting 1.2 pi. We could come up with a decimal approximation from this if we like. The units, again, are the units of the derivative, dA dt, and we're told in the problem that the area is given to us in square kilometers, time is given to us in terms of days, and so this is, the units here are square kilometers per day.